Hello and good afternoon, everyone. My name is Sherry Song. I am a physics graduate student at Princeton University in the United States, working for the SPIDER project. And today I'm very honored to be here to talk about the analysis we did from the first flight of SPIDER. We had our first B-mode result paper out on arXiv a couple months ago. And if you are interested in this topic, please take a look at it. So someone from the Cosmoglobe has introduced our program briefly on Monday. But for those of you who don't know about the SPIDER program, SPIDER is a balloon-borne CMB polarimeter to identify primordial B-modes on degree angular scales in the presence of foregrounds. So it is designed to measure R, the tensor to scalar ratio. And balloons provide a relatively low background, especially at high frequency for the galactic foreground observations. So if you look at the plot over here, the black line is McMurdo atmospheric spectra from 36 kilometer altitude. And in total, SPIDER has 3 bands providing spectral energy distribution of CMB observation. The 95 and 150 gigahertz were deployed in SPIDER 1, and we will have 3 280 gigahertz telescopes joining SPIDER 2. We also have a relatively large sky coverage from a balloon that's around 10%, and we have multiple modes with high fidelity from low L to L equals 300. SPIDER's first flight was from McMurdo Station, Antarctica, and it flew for 16 days to provide 12 LST days scientific data. We had 3 90 gigahertz telescopes and 3 150s with 2,400 transition edge sensors. The beam sizes are 29 and 41 arc minutes respectively. And in this first round of analysis, 4.8% of the sky was used. So in this talk, I'll be talking about the analysis pipeline result that our group did from this first flight. I'll jump directly into the time stream processing and go from maps to spectral estimation, foreground removal, and finally the recovering of the cosmological parameters. So we had around 2 terabytes of time stream from the 12 LST days. For our pipeline in the analysis paper, we divide these data into 10-minute chunks, and we flag the intermittent noises. On the right here, I show an example of a chunk of time stream. In the upper panel, the red is the data that has been flagged out. In a typical good channel, this data loss is around 10%. Then we have this quasi-stationary noise that is somehow correlated with the scan strategies in our timescale. It is similar to ground pickups from other experiments, but it's smaller than the amplitude of the dipole, and it changes with time. So right now we're using a 5th order polynomial filtering to that time stream. It is a aggressive filtering, and you can see the effect of that later in our result plot. I also want to note that we generate simulated time streams to construct simulated maps as references for our spectrum estimator later. For example, the blue time stream here is a reconstruction from a Planck map using our pointing and scan strategy. These can also be made into maps for comparison, and I'll show those later. Now, as we have the cleaned data, we can apply the calibration, which was derived by cross-calibrating degree scale power with Planck temperature data. We also, at the same time, estimate our beams by making these cross spectra with Planck. And then the calibrated data is combined with pointing and polarization angles to generate the 2-dimensional maps. We have a low-level processing paper coming out soon as well, and these details can be found in our main paper too. So as I showed in the previous slide, we can make simulated time streams from other experiments and apply the same flagging, filtering, beams, pointing, and polarization angles as SPIDER to generate what we call the reobserved maps from other experiments. For example, this is a temperature map comparison between a SPIDER 150 gigahertz map and the reobserved Planck 143 gigahertz map. The comparison between the reobserved Planck map and raw Planck map shows the impact of SPIDER's scan strategy and filtering that suppresses power at large angular scales. Can I pause here for a second? I will also put out our polarization maps here from the first flight. These are our Q and U maps for 95 and 150 respectively. The E mode pattern, so the Q and U directions are visible in these maps if you look closely, and is somewhat diluted by the galactic signal. Also, you can see that there are just more structure in the 150 gigahertz maps, simply showing that we have more foreground power there. Okay, so now we have the maps made. We're going to talk about the spectrum estimation next. We used 2 power spectrum estimators to analyze these maps. One of it is the XFaster pipeline, which is the main pipeline that we use, and it is very powerful. This pipeline is a hybrid of the traditional pseudo-CL method that follows the master formalism and a quadratic maximum likelihood estimator that iteratively solves to the maximum likelihood. In detail, it solves for band power deviations from a fiducial signal model using signal and noise Monte Carlo simulations. Since it is a maximum likelihood estimator, it just naturally yields an estimate of the Fisher matrix for the parameters. Some subsets of spider collaboration have been writing a paper about it, and this XFaster paper was also out on arXiv in April, and we have been working on the XFaster code package, and it is now on GitHub as well. The other pipeline that we use for comparison is a noise simulation independent pipeline. The idea is to straightforwardly use PoreSpice to analyze 14 maps created from 3 mini chunks compared to the 10 mini chunks and 4 maps for XFaster. And we estimate uncertainties internally from these many cross-spectral distributions. So as now we have the estimators, we should first use them to check for systematics in an experiment before we trust our data for actual scientific results. Hence, we need to do the null tests for spider using both pipelines. This is something that I personally have been working on in this analysis paper. So if you want to know the details on this, I can provide information. Null tests check for systematic noise residuals in the difference between pairs of maps and could be constructed in different splits of data by time or by detector set or other systematics that you care about. And we have done 10 different null tests for spider. Some are based on channel locations within a focal plane and others on time, for example, scan strategy and LST days. I'll take one for example. We do the inner outer radius null test because the beam shape would become more elliptical towards the edges. So this null test can probe that systematic effect. I will be showing 3 null test results from the 95 gigahertz data as an example here. Before I talk about these null spectra, I want to note that the multiple range that we use for analysis is between 33 and 257. These multiples are binned into 9 scientific bins with width of 25. And some outside bins are also estimated to account for the leakage into these scientific bins. So you can find it is exciting to have 2 completely different pipelines having results in agreement in the band powers and the chi-square numbers. Red is XFaster, blue is NSI. We used 4 covariants to compute these chi-square values, so the correlations in these band powers are also included. And the full table of these chi-square related PTE values can be found in the paper. And after accounting for the correlations between tests due to overlapping detector splits, for example, this one and that one, we are very confident to say that we have passed our null tests for both pipelines. So our data is reliable to be estimated using these pipelines. The next step would be to generate some raw spectra, and I'll show them here. This figure on the left is our filter transfer function and beam window function estimates. They are the average of the E and BB, which are similar but slightly different, because we had to use a aggressive filter to filter out our scan-related noise. As I mentioned before, the transfer functions look relatively suppressed in the lower Ls. And the figure on the right shows the raw power spectra from both pipelines for the full spider data set. The gray lines are the best fit Planck lambda CDM power spectrum. Since no foreground cleaning has been applied to these raw power spectra yet, so the points are expected to have excess power over the lambda CDM model, particularly on larger angular scales. So as CMB polarization measurements suffer from diffuse galactic emission, before we do any foreground cleaning, we need to think about which foreground matters for our experiment, and we need to validate that thought. A grad student, Joseph Vanderlist in our group, has done a harmonic domain study that fits models of the spectral energy distribution of foreground components to different experiments, SPIDER, WMAP, and Planck high frequency instrument. He fitted for 7 parameters using Monte Carlo Markov chains. These 7 parameters describe CMB, synchrotron, and dust, amplitude and spectral index, and the correlation, the cross correlation between dust and synchrotron, and the dust CMB correlation. We used flat priors for these parameters, except for the beta synchrotron prior from Planck posterior and dust CMB correlation prior from simulations. We did not fit for the synchrotron CMB correlation because it's expected to be the smallest of the 3 correlations, and the validations that we did indicate that we don't need that correlation. So after the parameters are recovered, we draw from the posterior of these fitted parameters and compute the EE and BB power spectra of the dust and synchrotron emission at our frequencies. As you can see in this figure, these points are the maximum likelihood point, with the arrow bars or the upper limits if you cross 0, being the narrowest 95% of samples around that point. This figure just tells us that we do not need to focus on synchrotrons at all in our spectral foreground cleaning, so we will focus on dust cleaning only. We used 2 separate methods to remove the foregrounds in our region. The first one is the template-based spatial removal. It includes a dust template that is made from differences between Planck high frequency maps and 100 gigahertz maps by assuming no spatial by assuming the spatial morphology of the dust is frequency independent. So you can simply scale the dust maps to match to a frequency that you care about and subtract that template out from spider maps. For example, these are raw maps from spider, and these are the template maps that we use, derived from Planck. Some very visible structures can be seen in both of the plots. The other method, SMICA, is done in the harmonic domain. It is a joint fit to all cross spectra among spider and Planck maps. It uses a rigid spectral energy distribution model for the dust, so no spatial morphology compared to the first method in the map domain. And you fit for the band powers of components to reach a maximum KL divergence between your data and the assumed model for your components, the CMB, the dust, and the noise. On the left, I'm showing a recovery of the different components that comes out from SMICA. It is a little hard to see clearly, but it's very interesting that each component is recovered pretty well, and they have different dominance in different frequencies as expected. For example, we can see that CMB is dominant compared to dust in the 95 auto spectra, and in 353, dust is dominant, comparing the dashed lines between red and blue. A full discussion of this method can be found in the paper, and we could provide more information in the upcoming foreground paper, so stay tuned. After we cleaned our foreground, we recovered our CMB polarization power spectrum. The XFaster and NSI points are using the template removal method, whereas Mika's results are the best fit component separated CMB spectrum. You can see that we have a good agreement between the different methods, and all pipelines remove significant foreground power in the lower L bins. It made the E spectra be in good agreement with the lambda CDM line. We next move on to the final result, which is the likelihood of parameters, and our key parameter here, the tensor to scalar ratio R. This is a likelihood result that comes directly out from our main analysis pipeline, XFaster. As I mentioned, XFaster is a powerful estimator, and it spits out the likelihood directly from maps, as long as we change the parameters we fit for. Here, in which case are the scaling factor alphas for the foreground template and R. We reached a maximum likelihood estimate of minus 0.21 for R here. We found that in our R equals to 0 input simulations, around 6% of the simulations have a R recovered smaller than this value. So with the expected noise fluctuations, this value is consistent with our simulations. Now, what do we how do we interpret this R value? We could do a Bayesian analysis, impose a flat prior and truncate it for R smaller than 0. And we got a 95% Bayesian limit of R smaller than 0.19. Or we could do a classical confidence interval for R following the Feldman-Cousins approach, where we simulate the R space with a 95% interval for each input R. Then we look at the certain R range that we have observed, and that gives us an upper limit of 0.11. I want to note here that in this plot, you can find pipeline-wise, XFaster recovers more information on R when we explore the R space with simulations. So this tells us that XFaster is the optimal pipeline to use among these two. And we, of course, apply these two interpretations to all three methods, XFaster, NSI, and Mika, to provide a summary of our likelihood estimations. This is the ultimate result from the first round of analysis from SPIDER-1. So we are actively working on more and better analysis of this data, and there will be more paper coming out on these topics, like the low-level processing, the transfer matrix, and the foreground phenomenology. We will put our band power and transfer functions to Lambda, and the XFaster estimator that we developed is also on GitHub, and I put the link here. I want to say that I am a senior grad student that has been working on both SPIDER-1 analysis and many years on SPIDER-2 instrument. SPIDER-2 has 3 new telescopes that are 280 gigahertz, and the cryostat that hosts it is currently in Princeton. It is ready for a flight. It will, of course, also be on a balloon and fly from McMurdo, Antarctica, and hopefully we can see this data in the next couple years. Okay, so to give a summary of this talk, we fly the SPIDER-1 on a balloon, and we got a tensor to scalar ratio R that's smaller than 0.11 or 0.19. There will be more interesting papers coming out, and we could provide better data from SPIDER-2 in the next couple years. Thank you, and that was the end of my talk.